When balancing chemical reactions, it's important to make sure that the species makes sense first. In other words, you want to make sure that the reactants and the products actually are logical. So, for example, sodium typically has a +1 oxidation state and nitrate a -1. And so that makes sense that there be one sodium and one nitrate. Similarly, we can look over here that say sodium has a +1 oxidation state. Since there's two of them and oxygen has a double minus state, that makes sense. And nitrogen covalently bonded would have no charge, and so the same would be said of sodium. So that all makes some sense. Next thing you want to do is you want to find something which is found in one reactant and one product. That's because the relationship would be fixed. So, for example, sodium would not be one to choose because sodium is found in two reactants. It's found as elemental sodium, and it's also found in sodium nitrate, and then it's found in sodium oxide over here. So we would not choose to start with sodium in this case. We could choose either nitrogen, because nitrogen is found only in the nitrate, and over here as elemental nitrogen, or we could choose the oxygen. In this case, we're going to choose the oxygen. There is 3 oxygens here, so that means we have to put a 3 here, with 3 oxygens on the left equal 3 oxygens on the right. Now what that does, that then fixes the relationship of sodium, because that means that there's 3 times 2 or 6 sodiums on this side, whereas on this side we have only 1 here, which means we have to put 5 out here. Now the only thing which remains to be balanced is going to be the nitrogens, and we can see that there's 1 nitrogen on this side and there's 2 on this side, and here we're going to apply a fraction 1/2. And the reason we can do this is because we're talking about moles, not individual molecules. And so if we wanted to balance this thing out in terms of reducing all of our fractions, we could multiply through by 2. So we essentially have 10 sodiums plus 2 sodium nitrates will yield here, in this case here, 6 sodium oxides plus 1 nitrogen. And now the reaction's balanced. We want to just go back and check to make sure that's all the case. And so if we say that there's 10 sodiums plus 2, that means that there's going to be 12 on the left, and we can see 6 times 2 is 12 on the right, so that works. Then we could look at the nitrogens. We see that there's 2 nitrogens on the left, there's just 1 times 2 or 2 nitrogens on the right. And then in terms of oxygens, we can see there's 2 times 3, that means there's 6 oxygens on the left, and there's 6 times 1 or 6 oxygens on the right. So we know that we're balanced. Now, a few more examples of this may make this a little bit clearer. So let's talk about the oxidation of glucose. Okay, so oxidation of glucose is what takes place in your body when in the mitochondria of your cells, which are respiring. So oxygen is going to combine with glucose, and the product from this is going to be carbon dioxide and water vapor. Now, we know that the reason we breathe is to inhale oxygen so that it can oxidize glucose, in other words, liberate energy from glucose to produce carbon dioxide and water vapor. So far, this reaction is not balanced here. But again, we want to look for something which is found in one reactant and one product. So scanning this right here, we can see that that carbon fits that role because there's just one substance here with containing carbon and just only one substance containing carbon over here. So if we keep this one constant, then we put a 6 over here, that means we now have 6 carbons on both sides. Now that adjusts the oxygens, but it wouldn't be good to go through and adjusting the oxygens right now because they're found in 2 reactants and 2 products, and therefore their ratios are not fixed. However, hydrogen is found only in the glucose in the reactant side and only in the water on the product side. So we can easily balance this. Since there's 12 hydrogens on this side, we could simply put a 6 in front of it on this side. And now we can go through and we can do our final balancing of oxygen. Again, we didn't change this, so we're going to assume that that just remains 1. In other words, there was no change in the coefficient there. So the only thing we want to change is this right here. Looking through at this, we can see that this side here has 6 times 2, which is 12 oxygens plus 6 more, so there's 18 oxygens there. We have 6 here, which means that we need 12 more, so we can balance this out by multiplying it out to 6. And again, there's no need to do any reduction and so forth at that point. Let's look at an example here of one that has some polyionic, in other words, where there's going to be ions that are going to be switching around. Let's say we take aluminum hydroxide and we're going to react it with hydrogen bromide. And the product here is going to give us aluminum bromide plus water. Now, some groups might tell you to, or some individuals might tell you to try to keep your ions together. Well, it doesn't really work all the time, and it's not good strategy to begin with. It's much better to look again at something where the relationship is fixed, where there's something which is found in only one reactant and one product. And we can see that in here in the case of aluminum, because there's only one case where aluminum occurs over here and one case where aluminum occurs over here. So this ratio is already going to be fixed. And we can put a 1 here and we'll put a 1 here. In other words, is that we have 1 aluminum hydroxide is going to yield 1 aluminum bromide. But the bromine is found here on this side in aluminum bromide. Here it's found in hydrogen bromide. And there's 3 of them here, so that means we need to balance that out. We'll put a 3 over there. Now we can work on the hydrogens and the oxygens. And let's take a look at the hydrogens. There's 3 times 1, there's 3 hydrogens there, and there's 3 hydrogens there, so there's 6 hydrogens there. The only place where hydrogen occurs here is in the water, so we need to multiply by 3 to give us 6 over there. And looking at this again, we can see that there's 6 hydrogens here. Now there's 3 plus 3, 6 hydrogens there. The oxygen, there's 3 oxygens here. 3 times 1 is 3. And we can see that, as before, that these things, that the aluminum and the bromine all balance out. Let's do one more here. Let's take a complex reaction, or I should say more complex. So let's take a look at a hydrocarbon. So let's say C18, H22, maybe something like in paraffin, wax or something like that, long chain hydrocarbon, is going to be oxidized. And we're going to produce from this, we're going to produce carbon dioxide and water vapor. And so looking at this, again, keep the strategy of finding something which is in one reactant and one product. We can see that there's carbon fills that role. There's 18 carbons here. There's none over here. I mean, there's just 1 there. So if we multiply this by 18, we now have 18 on the left and 18 on the right. The next thing to do is to go to anything else which is found in that 1-to-1 ratio, because that relationship is going to be fixed. We see 22 hydrogens here, and we see 2 over here. So if we multiply this by 11, we now have balanced our hydrogens. So there's 22 on the left plus 22 on the right. 11 times 2 is 22. And now we can see that we want to balance oxygen last. And again, the reason we want to balance oxygen last here is not because it's just oxygen, but because it's found in multiple products. It's found in both the carbon dioxide and the water vapor. And so its ratio is not fixed initially, but once the other ratios are established, we can fix that. So again, this is a 1 hydrocarbon chain here, and this we have 18 carbon dioxides and 11 waters. The only thing which remains to be balanced is the oxygen. 18 times 2 gives us 36 oxygens here, plus 11 here, so that's 36 plus 11, which is going to be 47, and now we can multiply by 47 halves. Just to reduce this out, we can multiply everything through by 2. That's going to leave us with C18H22. We'll have 2 of those, plus we'll have 47 oxygens, and that's going to yield 36 carbon dioxides plus 22 waters. And so by this process, we can balance reactions very simply, but again, the important thing to make sure is that everything makes sense in terms of the reactants and the products before we start to balance. Otherwise, our final balancing like this won't make any sense. So just to look at, for example, this one here where we have aluminum hydroxide. We know that one of the common oxidation states for aluminum is +3 and hydroxide is -1. So aluminum +3 is going to be balanced by 3 hydroxides so that the electrical charges there would balance. Again, we can look at the same thing here. Hydrogen tends to be a +1 and bromine a -1, so that makes sense. 1 hydrogen and 1 bromine would form hydrogen bromide. And similarly over here, aluminum has a common oxidation state of +3, tends to lose 3 electrons. Bromine tends to gain 1 electron, and meaning it would be negative. But since there's 3 of them, 3 negatives will balance our 3 positives. So that gives you some kind of idea for how we go through some basic stoichiometry, some basic equation balancing.